Today I've got a nice integral which is related to the harmonic numbers, one of my favorite number sequences, as well as one of Euler's constant, which is called gamma. It's sometimes called the Euler-Mascheroni constant. Okay, so we want to calculate the integral from 0 to 1 of 1 minus e to the minus t minus e to the minus 1 over t all over t. And like I said, we're going to need some facts. The first is the definition of the nth harmonic number, which is 1 plus half plus third all the way up to 1 over n. Next, there's this nice integral expression for the nth harmonic number, which I derive on a previous video. You should check that out maybe after this video. And that is the integral from 0 to 1 of 1 minus x all to the n power over x is equal to, like I said, that nth harmonic number. And then finally, we have this nice relationship between the natural log of n and the nth harmonic number. And that says that the limit as n goes to infinity of their difference is equal to this number gamma, which I mentioned earlier. Let's get started on this. I think you're really going to like this solution. It involves a lot of really nice tricks. We'll start by splitting up this into two integrals. So the first one will contain the first two terms in the numerator. We have the integral from 0 to 1 of 1 minus e to the minus t over t dt. And the second one will, well, it'll be what's left over. So minus the integral from 0 to 1 of e to the minus 1 over t, and then all over t dt. Now I'd like to perform a change of variables on this second integral to hopefully make it a little more similar to this first integral. And so here I'll take u and set it equal to 1 over t. But let's notice that means that du is equal to minus 1 over t squared dt. But then that'll be equal to minus 1 over t times 1 over t dt. Okay, and I decompose it like that because I've got this dt over t within the integral, so that's this portion right here. So that means I need to take care of this other minus 1 over t. But we can clearly see that here, this 1 over t is equal to u. Okay, but now taking this equation that I built, starting over here with the du, and ending over here with the minus u times 1 over t dt, we can see that solving for the leftover bit right here, this dt over t, maybe we'll solve for the minus dt over t, bringing this minus sign in here, we'll see that we get, let's see, it'll be 1 over u du. So that's the simplification that occurs. Okay, so let's bring that down. So we'll leave the first integral as is, so it goes from 0 to 1 of 1 minus e to the minus t over t dt. Then we'll have plus the integral of e to the minus u over u du, where I haven't done anything with the bounds of integration yet, and that's because those need to change. But how do they need to change? Well, let's notice as t goes to 0 from above, which is happening in this lower bound of integration, we will see that u goes to positive infinity. So I'll put a plus infinity down here. Then if t is equal to 1, u will also be equal to 1. So it looks something like this. But that's like a little bit out of order. It would rather go from 1 to infinity, so it's in order. So let's swap the bounds of integration and change that sign. So now this goes from 1 to infinity. Okay, great. And now let's recall this nice limit definition that we have for the exponential function, which we'll use for our next step. And that says that e to the something, so I'll just use box to mean something. In this case, the box will be minus t, and in the second case, the box will be minus u. So that is equal to the limit as n goes to infinity of 1 plus that something over n all to the n power. Okay, so I want to use that for both of these integrals. And so that will be used along with the dominated convergence theorem in order to exchange the order of integration and the limit. So now we'll have the limit as n goes to infinity of our integral from 0 to 1 of 1 minus t over n all to the n power. Again, we replaced box with minus t here, and this is all over t dt. Great, so that's our first integral sorted. And for our second integral, I'll write this as the integral from 1 up to n, sort of combining this upper limit of integration with this limit, so that's cool. And then we'll have 1 minus u over n all to the n power all over n. So we have something like that, and that's all occurring inside of that limit. Now I'd like to do a change of variables on each of these. And so for this first change of variables, I'll set x equal to t over n. Okay, but notice that means that t is equal to n times x, and thus dt is equal to n times dx. Okay, so let's see where that leaves us. We have the limit as n approaches infinity. We have this integral from 0 to 1 of 1 minus x all to the n power over, well, this is n times x, and this is n dx. So those n's cancel. So we have x and then dx right here. Okay, so that's good. And then over here we'll do essentially the same substitution, but just with different letters. So here I'll take the substitution x equals u over n. And that'll give us, we'll have minus the integral from, that will be 1 over n up to 1. So let's notice when u is equal to n, x is equal to 1. Oh, and I see that I made a mistake over here. This should be 1 over n. Because when t is equal to 1, x is equal to 1 over n. Anyway, so that's the bounds of integration sorted for these two integrals. And then here we have 1 minus x all to the n power all over x dx. So we're left with something like that. And let's recall that's a u, even though it's kind of messy. Okay, so we have our integral up here is now this limit of these two integrals. Okay, so now let's bring that up and then we'll finish it off. Okay, so this is where we left off. So we have the limit as n goes to infinity, this integral minus this integral. Let's notice that I put a big gap in the middle, and that's because I somehow want to build these out so that they can work together. Well, let's notice that this is going from 0 to 1 over n, whereas that over there is going from 1 over n to 1. Which means I could combine these in an integral from 0 to 1 of this integrand if I patch in a 1 over x in the appropriate missing location. Okay, so what will that involve? Well, it's going to involve adding and subtracting our special version of the number 1. And in this case, it'll be the integral from 1 over n up to 1 of 1 over x dx. So I'll add and subtract that in here. So 1 over n to 1 of 1 over x dx. So something like that. Okay, so now let's take this one right here as well as this one right here and put them into the same integral. And maybe let's do that off to the side. So these are going to combine into the following object. We'll have the integral from 1 over n up to 1 of 1 minus x all to the n power all over x dx. So we're left with something like that. But now, this integral that we've just built, together with this integral that we have, will combine to this fact over here. So let's bring this limit down. We have the limit as n goes to infinity of, now, like I said, those magenta underlines become the integral from 0 to 1 of 1 minus x all to the n power all over x dx. Good. And then this term right here is what's left over. So let's bring that down, and maybe we'll take the integral while we're at it. So that'll be minus the natural log of x evaluated from, let's see, 1 over n up to 1. But that evaluation isn't too tricky, and what you'll see is you get minus the natural log of n. So there are in fact 3 minus signs built into here, building this minus here. There's one right here. There's 1 from this lower bound of integration, and then there's 1 from applying the natural log rule because that's in the denominator. So that's why in the end we have a minus natural log of n. And then by our previous result that I recalled earlier, we have this integral. This first integral is this nth harmonic number. So we have h of n for that first integral. So in the end, we have the limit as n goes to infinity of the nth harmonic number minus the natural log of n, which, based off of our fact here, is that Euler constant gamma. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.